So hello and welcome in this video, and the topic of today's video is linearly independent vectors. Okay, so today we are going to discuss about the linearly independent vectors. Okay, this is a very important topic in the subject linear algebra. So before we start with the concept of linearly independent vectors, let us discuss what do we mean by the term linear combination of vectors. Okay, so first of all we will discuss linear combination, and after that we will use this concept to uh, obtain the concept of linearly independent vectors. Okay, so let we are having v1 v2 vn, so we are having n vectors here. Okay, these are n vectors, and we have if we consider this type of expression, alpha 1 v1 alpha 2 v2 plus alpha n vn, where these v1 v2 vn all are the vectors, and alpha i's are scalars. Okay, alpha i's are scalars. So this type of expression is known as the linear combination of vectors. Okay, so let us mark this as 1. So this 1 is known as the linear combination. Okay, linear combination of vectors. Okay, so in order to obtain or in order to check whether the given vectors are linearly independent or not, so the idea is we equate this equation 1 to 0. Okay, so what we are doing, we are just consider this alpha 1 v1 alpha 2 v2 up to alpha n vn is equals to 0. Of course, this 0 is uh, the 0 of the vector space from where we have taken these v1 v2 and vn. Okay, so we equate this let us consider this equation 2. So we equate this linear combination to 0. Now one thing is very much clear, that this equation, okay, equation 2 holds true if we are having, if alpha 1, if we put all these scalars as 0, if we put alpha 1 as 0, alpha 2 as 0, so if we consider these scalars as 0, then there is very much clear that that this equation 2 is true. Okay, so if this is the only possible case, if this is the only possibility, or you can say the only possible case, then the vectors are said to be linearly independent. Okay, but if we find some non-zero solutions, non-zero solutions, solution or solutions, then the vectors are linearly dependent. Okay, means if we have at least one alpha is non-zero. So if we are able to find some non-zero solutions, then our vectors are considered as linearly dependent. Okay, so let us take some problem on this concept. So for simplicity, we are taking the vectors from R3. Okay, so let us consider the vectors 1 1 minus 1 2 3 minus 5 and 2 minus 1 and 4, and we have to test whether these vectors are linearly independent or independent, right? So what we have to do, let us consider this as v1, this second vector as v2, and the last one as v3. Okay, so we mark this. Now what we have to do, we have take the linear combination. We have to take the linear combination alpha times v1 plus beta times v2, gamma times v3, and we have to equate, or we have to put this expression equals to 0. Of course, this 0 is coming from the vector space from which we have taken the vectors. So here these vectors are coming from R3. Okay, so this 0 is also belongs to R3, means this 0 is simply the 0 with components, three components as 0. Okay, so now we have put the values. So this is 1 1 minus 1 beta times 2 3 minus 1 plus gamma times 2 minus 1 4 is equals to 0 comma 0 comma 0. Now this will give you so let us take one more step here. So when you multiply this vector by alpha, so you will get alpha, alpha and minus alpha, and from here you will get 2 beta, 3 beta minus 5 beta plus 2 gamma minus gamma, 4 gamma, and these are equals to 0. Okay, so from here we can obtain, or let us have one more step here. So this is alpha, means the addition will be performed component wise. So we have alpha plus 2 beta plus 2 gamma, alpha plus 3 beta minus gamma, and minus alpha minus 5 beta plus 4 gamma is equals to 0. Okay, so when you put it to equal to 0, so we have a system. Okay, we have a homogeneous system of linear equation like alpha plus 2 beta plus 2 gamma is equals to 0, alpha plus 3 beta minus gamma is equals to 0, minus alpha, sorry, this is minus alpha minus 5 beta plus 4 gamma is equals to 0. Okay, now if we write it this system in the matrix notation as Ax is equals to B, so we obtain this as 1 2 2 1 3 minus 1 minus 1 minus 5 and 4. Here we have to put alpha, beta, gamma, and here we have to put 0. Okay, so this is a homogeneous system, and we are looking for the non-zero solutions, or means the solutions of this system. If we are having only the zero solution, then the vectors are linearly independent, and if we are having some non-zero solution, then the vectors are linearly dependent. Now this homogeneous system has a non-zero solution if, okay, so we have a non-zero solution. In fact, we are having infinitely many non-zero solution if exists. So we have non-zero solutions if the rank of the coefficient matrix A is less than n. So here this n is number of unknowns. Okay, here this n is number of unknowns, right? So here in this case we are having this n. Okay, the value of this n is 3, right? So if the rank of this uh, coefficient matrix is coming out less than 3, only then we are having some non-zero solutions, and our vectors will become linearly dependent. Okay, so now we have to obtain the rank. So in order to obtain the rank, we are going to apply our elementary row operation. So here we are applying R2 to R2 minus R1, and R3 to R3 plus R1. So this will give us, so since we are not applying any operation in R1, so there is no change in R1, while R2 will become 0, 1, minus 3, 0, minus 3, 6, and here we are having alpha, beta, gamma. Okay, 0, 0, 0. So basically we are using another method, which is the Gauss elimination method, in which we have forward elimination and backward substitution, right? Here we are not using this rank concept. Okay, so we are not using this rank concept here. We are using the Gauss elimination method. So now next we will apply R3 to R3 plus 3R2. So this will be 1, 2, 2, 0, 1, minus 3, 0, 0, minus 3. And this will be alpha, beta, gamma. Okay. And from here we are having 0. So now from here we again generate the system. So the system is now alpha plus 2 beta plus 2 gamma is equals to 0. From the second row we obtain beta minus 3 gamma is equals to 0, and from the last row we have minus 3 gamma is equals to 0. So from here it is easy to obtain that gamma is equals to 0. Once you put this gamma is equals to 0 in the second equation, so you will obtain beta is equals to 0, and when you put gamma and beta is equals to 0 in this first equation, so we obtained that alpha is equals to 0. So we have, so this implies alpha is equals to beta is equals to gamma is equals to 0. So as we are not having any non-zero solution, so this implies that vectors are linearly independent, right? Vectors are linearly independent. So let us take one more example here. Again, I am taking the case of the vectors of R3. So let us consider the vectors 1, -1, 1, and we are having 2, 1, 1, and lastly we are having 3, 0 and 2. So let us mark this vector as v1, this as v2, and the last one as v3, right? So in order to check this, again we have to make a linear combination. So again we will write alpha times v1 plus beta times v2 plus gamma times v3 is equals to 0. And again I am repeating the same thing, that this 0 is also coming from R3. So from here, if we put the value of v1, v2 and v3, so we are having 2, 1, 1 plus gamma times 3, 0, 2 is equals to 0, 0, 0, right? So from here we can again obtain alpha minus alpha alpha plus 2 beta beta and beta plus 3 gamma 0 2 gamma is equals to 0, 0, 0. So from here again we obtain a homogeneous system of linear equations. So this will give alpha plus 2 beta plus 3 gamma is equals to 0, minus alpha plus beta is equals to 0, and alpha plus beta plus 2 gamma is equals to 0. So again we are making the matrix representation here. So this will give us 1, 2, 3, minus 1, 1, 0, 1, 1, 2, and here we are having alpha, beta, gamma, and this is equals to 0, right? So now again we are using the same method, means the Gauss elimination method. So our first operation is R2 will be converted into R2 plus R1, and R3 will be converted into R3 minus R1. Okay, so this will give us the matrix as 1, 1, 2 and 3, while from in the second row we obtain 0, 3, 3, and here we are having 0, minus 1 and minus 1. Okay, and here we are having alpha, beta, gamma, and on the right hand side we are having 0, 0, 0. So here if we apply R3 to R3 plus 1 by 3 R2, so you can see that this is 1, 2, 3, 0, 3, 3, and this row will become completely 0. Okay, so here this is the case when the rank of the coefficient matrix is coming out 2, means which is the number of non zero rows in echelon form. Okay, in echelon form. So which is certainly less than 3, which are number of unknowns. Unknowns means alpha, beta, and gamma. So in this case, here we will have infinitely many non-zero solutions. Okay, infinitely many non-zero solutions. So in this case, the vectors are linearly dependent. Okay, so this is how we can check the independence or dependence of the given vectors. Okay, so this is some basic idea about the linearly independent and dependent vectors. Okay, so that's all for today's video.